So this is basically an introduction to high voltage engineering, and I'd like to start from the power system. Power system starting from the generation to the transmission to the distribution to the load. Some of you are working in these areas. Some of you are doing some studies like load flow studies, load flow, short circuit, contingency analysis, and so on and so forth. You do that sometimes at the transmission level. You do that at the distribution level. Some of you might work on studies how installing a renewable energy, how this will impact. So that is basically when you study at the system level. Now, high voltage engineering, when it comes to the power system, we deal only with the assets. So we deal with the generator, we deal with the transformer, we deal with the overhead lines, and so on and so forth. So power system assets, for us, we look to it as a component. We don't care much about their performance in the system. But for a system engineer, it is also very important for them that they understand this link. They understand what are the weak points of the asset, what can make the asset fail, because if an asset fail, this would impact the power system. So you should not look to the asset as a black box. No, you should have an idea about it. And that course trying to explore the different aspects of the power system assets. So when you look to the asset, we're starting from the design of that asset to the manufacturing, to the testing, and then the condition monitoring as you put it in the or install it in the field. So the high voltage engineering has to do with all these aspects from the design until you install it and you start to age in the field. So when we talk about the design, there are different design parameters that you need to take care of when you design a power system asset. There is an electrical design, of course, because it's an electrical. For example, let me think about the transformer as an example, and the reason for that because I worked in a factory of a transformer for 6 years, so I have very much many practical issues about transformers. So when you design a transformer, there is the electrical design, so you have to select the conductors, but also you have to select the insulation. So selecting and designing the insulation, that is the part, or this is the job of the high voltage engineer. Then there is the magnetic design. As we know, the transformer has a magnetic circuit, and mechanical design as well, and we'll see the impact of the mechanical design of the transformer. But part of the mechanical design is designing the tank. Part of the mechanical design is designing the winding so that if there is any force coming due to short circuit, it should withstand that. There is also the thermal design. Sometimes high voltage people get involved with this. Sometimes pure mechanical engineers do work on that. There is in the transformer, there is a heat dissipation because you have losses coming in the winding, coming in the core. There is heat. You want to dissipate this heat efficiently, okay, so that the transformer temperature should not exceed certain value. So that is the thermal design. And as the transformer getting bigger and bigger, becomes more and more complicated. Okay, so but for us as high voltage engineer, the insulation design is very important, and more specifically, we want to know the electrical stress. And that is the job of the softwares like COMSOL, for example, or ANSYS. They help you to calculate the electrical stress so that you will know at the design stage what is the stress on the different insulating materials. And by knowing the physics of this material, you will know that this stress, is it high or is it acceptable stress? Then we have the manufacturing. Now, when you manufacture the transformer or any other component in the power system, you usually manufacture separate components. For example, in transformer, you do the winding by itself, you do the core, you do the tank, okay? So there are different things you do, the winding, then you assemble them. And as you are doing the manufacturing of the different components. Now the insulation is part of it. In the transformer, you have the oil, you have the paper insulations. So you have to, during the manufacturing process, you have to know, even as a technician, that what are the things that will impact my insulation system. For example, you are filling the transformer with oil. You have to understand and know that oil and water shouldn't come close to each other. So if, for example, if your factory is at high humidity level, you have to make sure that you are degassing, or make sure that there is no moisture mixed with the transformer oil. Now for the testing, in transformers or any other things, usually the testing done in 3 stages. We have the incoming material testing, and when we talk about specifically the electrical insulation, because that is, as a high voltage engineer, that is our interest. For example, oil, we take samples for the new oil and we test. Sometimes we test the breakdown voltage, sometimes we test the water content, sometimes we test the acidity, and so on and so forth. Even for new oil, sometimes we want to make sure that we take a random sample and we want to make sure that the oil meets certain standard. Then in process, now as we are doing the different stages of the transformers, you want to do different tests, mainly your technical dimensions, so that you make sure that when you do the assembly, you are reaching the assembly stage, there is no big issue. But also, one of the tests that we do in process, we do the Megger test. Because in the manufacturing of the transformer, we do sometimes when we connect the winding with the core, to prevent any moisture, we put the transformer in an oven to get rid of the moisture. To make sure that this process was active, we measure the electrical insulation. So that is a high voltage job. And then finally, we come to the final product. I will give you some examples later on about what are the tests that we do in the transformer that is relevant to us as high voltage. Okay, so you have the product designed, manufactured, tested, ready. So you see here the high voltage comes at different stages. Then you deliver your transformer or your electrical product to your customer. Then it is the customer job is to actually keep on monitoring the condition of the assets, because you don't want this asset to fail suddenly, and you don't have a plan for that. Here comes the condition monitoring. Some utilities use the old technique, which is time-based, meaning that they do testing and inspection at certain time intervals, every year, every 6 months, every 2 years. It depends on the utility practice. But people moved from this time-based because they found that this is really not efficient. So we used condition-based. So based on the condition of the asset, you will have more regular inspection, or you have more far apart inspection. And here comes how I can decide the asset condition. And here's something very important. We need to know that the most important part in the asset, from conductors, from tank, from insulation, that will decide the life of the asset is the insulation system. Why? Because it is the weakest part. So the insulation system is something that you need to pay attention to it. Now, based on the assets, we need to know what are the tests that we need to measure so that we can evaluate the asset. And here comes in the term paper, that is exactly where you want to focus. Then the last paradigm of condition monitoring comes the reliability based. So it's not just the condition of the asset, but how critical this asset to the whole grid, to the power system. I have 2 transformers. Both of them are in a bad condition. However, one of the transformers is connected to very critical loads. It's in downtown. If I lose that transformer, the loss as a result of the failure of that transformer will be huge. I have similar transformer, but connected to very remote load, not much load connected to it. So if I lose that transformer, not a big deal. So now when I want to put my priority list, if I have a constraint in the budget as a utility, then I will give a priority for that transformer that has bigger impact on my power system. And that specifically, this paradigm of condition monitoring is very, very important. And this is the link, one of the links between power system and high voltage engineering. Now, with this overview about the relationship between the high voltage in different aspects of the assets, let's go now and see what are the sub areas in high voltage engineering. High voltage engineering, can, you will see people with different backgrounds. You will see electrical engineer, you will see physicists, chemists, and sometimes even you see mathematicians. And each one has certain roles in the high voltage area. So the high voltage, it has, as I said, let's go back here from the design, manufacturing, testing, and condition monitoring. So the electric field calculation, this is the tool you need at the design stage. Okay, then you will need to test those equipment, but to test them you have to understand what are the sources that we use, and we'll talk about that. This is the generation and the measurement of high voltage. Now, as I mentioned, the most important part from our perspective as high voltage engineers is the electric insulating materials. So I have to understand the physics of these electrical insulating materials. I have to understand what are the tests that I need to do to evaluate their conditions. And as they age with time, what will happen? What are the failure mechanisms that can happen at that specific materials? And we will talk about different aspects of that. Of course, condition monitoring, this is one of the, I would say, one of the most important areas in high voltage engineering right away at these days. Why is that? We live in North America. We have many of the assets have exceeded or about to exceed their life. Transformers, cables, insulators, and so on and so forth. The question is, I have limited budget. So I have to have a priority list. Which asset I have to change? Which asset I need to refurbish? Which asset I can keep in my system? So that is a very hot area nowadays, and there is a lot of research, and I will talk a little bit about it today, but in details later on. So we'll start with the electric field. Why do we start with electric field? Because this is the design. This is the starting point. So we will start with the electric field and see what is that. So this is a snapshot of electric field calculations using COMSOL. So basically here, this is a cable joint. And in the cable joint, there is certain areas will have a high electrical stress. And these are some of them. And we'll talk about that later on. When we have a water droplet on a surface of insulation, these we call them tripling buoyants, and those tripling buoyants will have a very high electrical stress. Now, this is something very important. So when we design an outdoor insulation system, we have to be aware of this. So what will happen if the insulation is dry or if it is wet? How much electrical stress can be generated, which can start some arcing on the surface of the insulator? This is the electric field of bushing. And by the way, all these diagrams is for the electric field or for the potential. Okay, so that is the most important thing to do as a high voltage engineer, is to model your device. You want to see where is the highest stress. Is the stress high enough to start to cause ionization or failure of the equipment? And if yes, if it is high enough, how I can relieve this stress, how I can reduce that stress. There are certain techniques, we'll talk about them later on. So that is the first aspect, the design stage. Then we need to understand the electrical insulation material. And every power system asset, they will have different materials. Some of them, as we will see, have one specific material, Some of them, no, they have hybrid materials. So you should be aware about those insulating materials. What are the properties of these materials? What is the aging mechanisms of these aging materials as we progress? So I will give some specific assets. Again, I will start with the transformer. Transformer, they have all different types of insulating materials, which can be categorized as three: gas, liquid, and solid. In transformer, you will see all of them. So when we have here a bushing in the transformer, this is high voltage here, and the tank is actually grounded. Okay, so you have to maintain certain what we call creepage distance between the high voltage and the tank. Otherwise, they will have a flashover. Another issue that you need to understand, what will happen if the surface is polluted? And if the pollution has sort of salt in it or conductive materials, then you will start to have an electrolyte once you have high humidity or drizzle. Then you will start to have an arcing on the surface through until it reaches to a complete flashover. So you have to understand how to design this bushing, what should be the creepage distance based on the high voltage and based on the pollution level in that specific area. Also, the transformer is filled with oil, and oil is extremely important, and this is a liquid form of the insulating material. Now, oil basically does two things. It will cool the transformer, I mentioned that earlier, and also it will electrically insulate the high voltage from the tank, which is grounded. And basically we have three different types of oil available nowadays in the market. The most common one is the mineral oil. It's a hydrocarbon oil. It is the cheapest one. And it has very good advantages. However, the major issue, or one of the major issue in mineral oil is first, they are from crude oil, and at certain time we know that this material will vanish. So we need to have replacement. Second, it's a flammable. So at certain temperature, the oil can catch fire, which can be very catastrophic, especially if this is like in a high-rise building or if it is close to some critical load like hospitals or schools. So these are some limitations in the mineral oil. We have synthetic oil or silicone oil. Now, this is a hydrocarbon. This is not a hydrocarbon oil. This oil has an advantage over the mineral oil that the flammable temperature is much, much, much higher. Okay. However, this one has certain disadvantage, which is the cost one of them. Then we will have the ester oil or vegetable oils. And this oil is basically a new trend in the transformer from different vegetables. Now, this oil has the advantage that is coming from natural resources, but still we don't have experience with that. Recently, some utilities, especially in Australia, they start to share their experience after this 10, 15 years of experience. What are the problems that facing this oil? So all of this is just one insulating material. As a high voltage engineer, if you are dealing with a transformer as an asset, you have to have a good idea about this. Finally, transformers also, they have a solid, like a breastboard, like these are breastboards. This is a breastboard. This is a three-phase transformer. Okay. There is also winding insulation. Now you see this is in the last layer. This is the high voltage winding, and we use mica to insulate the conductors. Sometimes we use paper to insulate the conductors. So this is another insulating materials. There is, if you see here, this material, you see this, like we call it epoxy diamond paper. These materials, when you put it in the oven, the diamond will be activated and it will be gluing. So this will give a very mechanical strength and a good insulation for this. So cellulose paper basically is one of the most important factors that decide the life of transformer, not the oil. Why? Because the oil, I can take it out, replace it, or refurbish, degas it. Okay, start working as new. But once the paper age, you cannot do anything about it. You cannot unwind the transformer because the cost becomes huge and there is no point to do that. Then basically you need to replace the whole transformer. So you need to understand what are the tests. Like for example, one of the most important tests, we call it degree of polymerization of those insulation paper. Once it reaches certain value, then becomes very weak. The material brittle will be very brittle, and mechanically they can fail if there is any mechanical stress on those transformers. So these are all important information about only one asset. Let's move to another asset, outdoor insulators. Outdoor insulators, we have two main types. We have ceramic and we have polymer. Ceramic, we have porcelain and glass. This is the old technology. Okay, so we are comfortable with this technology. We know its pros and cons, more than 100 years of usage. One of the major issues with those insulators is their pollution performance. Okay, that once they are wetted, there is a wetting on the surface of these materials, there is a leakage current, and there is a flash over. How we can solve this issue? By washing the insulators. Now, sometimes, especially in high humid area, highly polluted areas, that is not an economically good solution because the cost become huge in certain area in the world. You need to do the washing every 6 weeks, sometimes every 2 months. And imagine that those transmission lines, you have them for hundreds of kilometers. So that is a lot of cost. Then this comes the new solution is to use the polymer insulators. And when you look here, this is made from silicone rubber material. And when it is wetted, the surface of the material, we call it hydrophobic. So you see here the water droplets, they do not combine together. You don't have a wetting surface. You have discrete water droplet, which will prevent any arcing on the surface. So that is an advantage of this material. However, one of the things that we know about this material, it ages with time. And the aging is different based on the environmental conditions, based on the pollution severity, and so on and so forth. So this is another example of a material. As an engineer, the decision which type of material to use, understanding the pollution performance, can affect your whole power system. Let me give you an example. The outdoor insulators, only 5 to 8% of the cost of the transmission lines, but around 60 to 70% of the failures coming from outdoor insulators. So although their cost is not that high, their impact on the power grid is huge. So you have to understand as a high voltage engineer how this material works and how I can improve their performance. Another type of insulating material that has solid and gas insulation is gas insulated substation. This is a GIS system at 400 kilovolt system. So this is, I took the picture myself for these ones, 400 kilovolt. Now, those GIS are filled with SF6. Now, SF6 has a very important feature. We call it, it's an electronegative gas. What does this mean? It means in simple language, SF6 can absorb electrons, but still act as a stable material. Normal material, when you absorb electron, the atom gets excited, then you have to release this electron again. However, SF6 can absorb the electrons. And why this is important? Because the flashover or an arc is basically a flow of electrons. So if the insulating material can absorb these electrons, they can extinguish any possible failure in the system. So they are a very good insulating materials. But also there is as well a solid inside. Now those GIS here inside, there is a high voltage conductor going through them. Okay, I mean, the reason why we are using this GIS system is to reduce the size of the substation. Now, how to hold these conductors? We have the spacers. Spacers is basically a dielectric material or an electrically insulating material that insulate the high voltage from the grounded structure. Now, sometimes there is failure happened. Some surface discharge happened that caused the whole failure of the substation. How to improve this material, how to understand their performance, that is something very important for the high voltage engineer. Also, we have the bushings. Bushings, now they act like in transformers. So in transformers, as we have the air, we have the creepage distance, same thing here for the bushings of the GIS system. Then we have underground cables. All technology, we have impregnated paper oil. Still we have them here in Canada. Very, very old systems, but still they are working. So this insulation system, because here we have high voltage, here we have a ground. So in between we have this electrical insulating material. We have to understand their aging performance. We have to understand how to diagnose its status. The newly material, which is the relatively new, of course, the cross-linked polyethylene, or for short, XLPE, like this one. Now, this is the high voltage, and here is the ground, and this is your XLPE material. Now, this is a better material, better insulating material. Nevertheless, again, like any insulating material, the age. There are some failure mechanisms like water treeing, electrical treeing. You have to understand this. You have to understand what are the problems in the manufacturing stage. What are the problems that as the material age with time, what are the testing that we have to do to ensure that the material has no big flaws that can cause immediate failure of the insulator. Finally, rotating machines. They have a different set of insulating materials. So this is basically one coil. This is a coil of high voltage motors. Okay, so we have ground wall insulation system. Now, as those conductors will go through the core, which is grounded, so we will have here ground, which has zero potential, and has a high voltage. So high voltage, when it comes close to the ground, you will have a very high electrical stress. Okay, so you have to select proper materials. Not that only, but usually, especially for high voltage rotating machines, you have small conductors, and these conductors, turn to turn, you also insulate them using some certain papers. Also, we have what we call the stress grading material, and we will see the importance of these stress grading materials as we progress in this course. Any question here so far? Anything that not clear? Anything that you want to ask about? Okay, so now let's go and start talking about the generation of high voltage. This is something very, very important, that we need to generate different forms of high voltage. Why is that? Because our power system asset components, they could be under AC or under DC. Do we have equipment under DC? Yes, of course. We have underground cables, we have overhead lines under DC, and DC system now becomes more and more popular, especially when you want to transmit a huge amount of power for a very long distance. It becomes more economically to do that under DC system. And this is one of the, I would say, a hot area in high voltage electrical insulation, because we are used to the AC system, but we are not used to the DC system much. So in the DC system, there are different forms of aging and more severe stress on the insulating material. So it's either you are putting the material in or DC system. Before you install them, you have to test them under the AC or the DC voltages. So then you have to generate this AC voltage or this DC voltage. Plus, this is the steady state stress. This is the stress that exists 24/7. But there are some other stresses, we call them transient. Could be because of something happen in nature, like lightning. When a lightning hit an overhead line or a power system asset, there is a very high voltage happens there. Also, whenever I do any switching, if I switch a capacitor, if I switch off a load, there will be some sort of transient as well. So my asset, although they are supposed to work in AC or DC, now they are subjected to some sort of transients. So I have to make sure that these assets can withstand this. Then, or so I have to have generation of high voltage under these different voltages. This diagram show to you that how much over voltage in per unit I could have under these stresses. So for example, in lightning over voltages, I could have up to 6 times more than the rated voltage. Switching, I could have 4 to between 2 to 4 per unit. Also, there are some sort of short over voltages due, for example, to single line to ground fault. Whenever you have a single line to ground fault, the voltages at the other phases increase as well. So the equipment or the asset are subjected to an over voltage. So before we deliver the material to the customer, I have to make sure that my asset will be able to withstand those over voltages in the system. So for this, you need to basically test them under high voltage. These are high voltage testing transformers. This is a transformer that we have it here at the University of Waterloo, can test up to 400 kilovolt. Now, sometimes you need much more than this. Then you cascade the transformer to get a voltage higher than the 400 or 300 kilovolt. There is limitation per unit you can get out of the transformer. Otherwise, it becomes bulky. So you can cascade transformers, and these things will be talk about them later when you talk about generation of high voltage. Impulse, again, this is something, as I mentioned, it's very important, it's very critical. We need to test the equipment against different types of impulses. We talked about lightning and we talked about switching. These are surges that stays for a very short period of time, micro to milliseconds. So I need to mimic this in my lab. I need to test my equipment before I give it to the customer. I want to make sure that they can withstand those type of stresses. DC as well. So this is a 300 kilovolt DC supply. Again, can give you plus or minus, depends what polarity you want. This is available also at the University of Waterloo. This is another example of high voltage DC supplies. Now, all these supplies, there are people only working on this. How to design a high voltage DC supply or how to design an impulse generator. So the design of those generators are extremely important in the high voltage engineering. Now, when we generate those high voltages, I need to measure them. Okay, how do I know that the voltage is 250 kilovolt? I have to measure the voltage. And in measuring these high voltages, we use the simple principle that we use it to measure in the low voltage as well, which is using the voltage division. Very simple technique, but it's very, very efficient. So for example, if I want to measure, let's say 220 volt to my oscilloscope, okay? So I cannot plug in 220 directly. Maybe I can go up to 10 volt or 20 volt only. So I need to step down this, and by selecting proper R2 and R1, I will have the needed voltage to be stepped down using simple voltage division. So your V out will equal to the Vn times R2 over R1 plus R2. R1 plus R2 is basically the total resistance of this. Okay, so by properly selecting this, I can step down the voltage to the level that I am really interested in. So that technique, we use it in low voltage measurement, but we use exactly the same technique to measure in the high voltage. So this is basically, this one is a voltage divider. This is another voltage divider. These are pictures taken from the University of Waterloo. This is for the impulse. This is for the DC, and we have different types of voltage dividers. We'll discuss them in details. We have capacitive, we have resistive, we have combined between capacitive and resistive. What is the pros and cons of each one? That will something that we'll discuss later. Now, because we deal with very high voltage, the size of those voltage dividers will be very, very high. Now, they are not just two simple resistors that we can build in the circuit. No, these are huge, because if I just have a small resistor in terms of the size, you will have a flashover. So I have to increase the size. And once we increase the size, there are some other issues, like the stray capacitance will take part, and we have to pay attention to this. There are certain issues now start to appear. They don't appear in small voltage dividers. Now, in the substations, basically nowadays, the main technique we use capacitive voltage transformers. These are two examples. I took them from two substations. One of them, this is at 138 kilovolt, and this is at 69 kilovolt. Now, in high voltage course, we are more interested to those voltage dividers, not those. Those are more used in the substation design. So we'll not talk about them in this in a typical high voltage course. But I just want to bring them to you so that you understand that we always need certain types of mechanism to reduce the voltage so that I can measure my high voltage. Also, I need to measure the current. In simple circuits, one way to do that is to insert an ammeter in series. Okay, so that's an emitter. So there is some, these are the jacks for the ammeter. So you connect it in series. Now, that's not very practical, especially in high voltage circuits, where you need to interrupt the circuit every time you need to measure the current. So basically, we use a clamp. A clamp is a much more practical way, but this is, I'm talking about low voltage. This is all low voltage, but we use the same technique. This one, the clamp one, or the donut, so we can measure the current from the induction, because once you have a current, you have a magnetic field. This magnetic field will induce a current in my measurement devices. So these are some two examples of current transformers. This is at 138 kilovolt substation. This is at 33. So these are the current transformers that we have. We see them here, and these are the current transformers in outdoor substation. This is in an indoor substation. Now we will talk about current measurement a little bit later on, but the focus will be more in high voltage, because high voltage is basically the most important thing for high voltage engineers. Okay, so now we know about the design of the materials, of the assets. We know the assets weakest part that we need to pay attention to is the electrical insulation. Then we need to test them, but before testing them, we need to design the high voltage supplies. And we know now there are three types of them. We have AC, DC, and impulse. And also we need to do the measurement for those voltages and currents. Now comes the testing of those assets. So the testing, generally speaking, can be classified to routine, type, and special tests. Routine means that every single component or every single asset has to be tested. So every single cable, every single transformer, every single installation has to be tested. This is why called routine test. Then there is a type test. In the type test, you have to test every single design. And usually you have a certificate coming from certain labs, international labs. Usually customers ask for independent labs, like Kima, like Chessy, like those type of big international labs. We have Kinetrix here. So you keep a certificate for every single design. So you don't need to repeat the test every time when the customer comes to you. You want to show a proof that This design has passed those type tests. Then there is also sometimes in some assets we have something called the special tests. Those special tests, they are not routine, they are not typed. This is based on agreement between you and the customer. The customer might ask to do one or more of those tests. So I will take a transformer as an example, and I will highlight some of those routine tests, type tests, special tests, and I will stress on the tests that are relevant for us as high voltage engineers. So routine test, we have the no load test, the short circuit test. These ones, we do them to measure the losses in the transformer. This is measure the core loss, and this is will measure the copper loss. This is the basic things. We need to know the losses of the transformers. Also, we measure the DC resistance of the winding, but the test that is of interest to us is the high pot test, or sometimes they call it the SSV test, the separate source voltage test, or the and the induced over voltage test. These tests will be discussed later on in details, but for high voltage engineers, these are the routine high voltage tests that you have to do in every single transformer. Type test, we have two main type tests in transformer. We have the heat run. In the heat run, I want to know what is the maximum temperature can be reached by the oil and by the windings. So electrical engineer can do understand this, but this is more, as I said before, for a mechanical engineer. But the impulse test, this is the test we conduct to make sure that transformers can withstand any transient that might happen from lightning or from switching. So that is the high voltage test among the type tests. For the special test, there is the short circuit test. Now this short circuit test is different than this short circuit test. This test, we apply a reduced voltage to allow the rated current to pass through the transformers when their secondary is basically short-circuited. So we apply only 4 to 6% of the voltage. So it's just we allow the rated current. But this special test, here you apply rated voltage when the transformer is short-circuited. So you will produce much, much higher current. What will happen? You will have a very high force. Whenever you have very high current, you will have very high force, and this will induce mechanical forces on the winding. So that is would test the integrity of your winding, mechanical strength. Now, the weak part in the transformer is the papers. This is the weak part. Conductors are strong mechanically, but the papers is the weak part. So you need, as a high voltage engineer, to understand a little bit of this, to design it so that the insulation is good enough. So they are, because to have high insulation, you have to have more papers, okay? More layers of papers. But more layers of papers will lead to weaker mechanically winding. So it's a compromise how you can achieve both goals. Also, the partial discharge. Now, in distribution transformer, that is not a standard or routine test. If you go for high power transformers, this could be like a standard test. Now, the partial discharge is also a test that high voltage engineer need to do that. So this is one way to look to the tests. Is it routine? Is it type, or is it special? Now, when you look to those tests, the high voltage tests, we can classify them as two different types of tests as well. Now, these are the tests basically from the insulation perspective. So it is our test, our high voltage test. They could be destructive. What does mean by destructive? Destructive, it means that the test or the asset either pass or fail. Nothing in between. The test will not give you the quality. How good is your asset? It will tell you that your asset passed the test or your asset failed the test. That's all. And these are some examples. The AC high pot test, the DC high pot test, the impulse test. The conclusion in the test certificate, pass or fail. But there are some other tests will test the quality of the insulation. We call them non-destructive tests. So the intention here is not to the pass-fail criteria, but the intention here is to know the quality of the insulation. So something like the partial discharge, tan delta, insulation resistance, and these tests will be discussed in details later. It will give you an idea about how good or how bad is your insulation, especially after aging. After aging, these values will change from a new insulation system. So to assess the aging of the insulation system of your bar system asset, these are some typical examples of the non-destructive tests. Finally, we'll talk about condition monitoring and diagnostics. Now, that's a huge field, and depending on the asset, there are several tests, each one. These are some just examples. Online, partial discharge monitoring, transformers, cable, GIS, generator. While the system or the asset is energized, you go and you try to detect if there is any partial discharge. Dissolved gas analysis. When the oil of the transformer age with time, there will be some certain gases dissolved in the transformer oil. So you want to go there and basically you want to analyze them because they are indicative of different types of fault that happened in the transformer. Oil testing, there are different tests like breakdown, humidity, or water content, interfacial tension, acidity, and so on and so forth. This also gives you an idea about the quality, the overall aging of the transformer. So dissolved gas analysis will give you if there is a certain fault, specific fault happening, but the oil will give you the overall aging of your transformer oil. Leakage current measurement for outdoor installation, for bushing, will tell you how bad is the surface in terms of pollution or in terms of physical damage. These are some projects my students were involved in. So this is a project we did with Kinetrex. This is an RF antenna. So we are trying actually to monitor some insulators with some different defects. Because when there was some defects, there will be some radiation of electromagnetic waves. We are trying to capture this using the RF antenna. This is another project we did it with Kahrama, the utility in Qatar. We are trying to monitor the partial discharge inside the transformer using acoustic emission sensor. So these are basically if there's any discharge inside, there will be some waves, acoustic waves inside, and these can be detected using those acoustic emission sensors. What is the new trends or what are the new trends in condition monitoring and diagnostics? And these are some ideas for some term paper as well. Using of drones. Drones now becomes very popular. There are many applications in them, and one of them is basically to monitor the health conditions of your power system assets. Utilization of multi-sensors. Now, every sensor we use has certain limitations, has certain pros and cons. Now, we are trying to combine multi-sensors and integrate them in such a way that you have exposure or access to all different types of defects. So how I can minimize the number of sensors and at the same time get exposure to all different types of defects. That is also a new area. Finally, the application of machine and deep learning. This is something very recent nowadays used, and that can really help the scarcity we have of experts in the field of high voltage equipment assessment. Now, with the machine, you can solve a lot of condition monitoring problems because you acquire a signal either coming from an RF antenna, IR camera, ultraviolet camera, but then you need to analyze this data. You rely a lot on an expert to go and analyze this data. Now, what if I don't have that expert? So an online smart system can help me to replace that expert to a certain extent, of course. Okay, what if I can add the algorithm with the drone? So the drone, they don't just go and do inspection, but they do inspection and diagnostic on site. So they have some certain sensors, take these sensors to the microcontroller where you have your algorithm there and analyze the data and come up with a conclusion that, okay, there could be some crack in that insulator, or there's a pollution problem here, or the bushing of the transformer has certain issues, and so on and so forth. So this is an overview about the link between high voltage engineering and power system